It's okay. So, good evening, everyone. I'm just waiting for some time. If anyone wants to join, mm, let's see participants see are there. Then I will start. I'm just working on a 2 minute explain, and I will start from 5 p.m. Okay, so we can now start. So this is uh, week two, and I am going to discuss about the assignment two problems. And so myself, Ramya Mandal, I am a PMF scholar of IIT Roorkee, and I am working under Professor K.L. Yadav. Um, and today I am doing PMF TSC, Teaching Assistant Secretary, for the NPTEL course of Fundamental and Applications of Dielectric Ceramics. Okay, the course code is NL31 and course instructor is Professor Ashish Garg from IIT Kanpur. Okay, so we can start from. So what we have learned in week two, uh, you have already learned in week two some basic introductions of Pauli's rules, Pauli's rules according to crystal structure of ceramics. It's mainly decides the ionic crystal structure, and we will discuss its regarding problem and its so some five rules of ionic structure. Next, we have also studied about ceramic materials and its crystal structures. Some ceramic materials like AlO2, AlO2O4 structure, perovskite structure. Okay. Next, you also have learned about the defect chemistry and the defects chemistry like non-stoichiometric oxides, stoichiometric oxides. We also discuss about some problems regarding this and some concentrations and effect of intrinsic impurities. Some impurities and these effects, everything has been described in week two. And rest the problems will be from week one uh, week 2, and I'm just starting question number 1. Okay, so question number 1, just read the question carefully. In ionically bonded ceramic structures, ionically bonded ceramic, what type of ceramic? Like sodium chloride, some oxide, magnesium dioxide, okay, aluminum oxide, iron oxide. Okay. So these are the ionically bonded ceramic. So you have already learned in week 2 about the structures. And so there are four options there. It had been told that which of the following is true. We have to find which of the following among these options are true. There may be one option true. It may be more than one options true. Okay, you have to find out. So it told about the cation anion sublattices. Okay. Uh, cation makes base lattice and means cation anion in which position they occupy, how they are arranged, okay, and how closely they are packed. Okay. So for this concept, to know all this concept, you have to learn about the Pauline's rules. Some Pauline's rules, which mainly tells about the ionically bonded ceramics and their arrangement of cations and anion arrangement in ionically bonded ceramic structure. So Pauline's rules is given by Linus Pauling in 1929 for predicting and rationalizing the crystal structure of ionic compounds. He gave 5 rules, 5 important rules. Okay, so let's already you all have learned about Pauline's rules, 5 rules. Again, I am just telling about some rules. Okay, just 1 minute. Wait, but means it's okay. Okay, it has been. Okay. If you have any question, you can write in message section. So first rule is uh, radius ratio rule. For typical ionic solid, cations are smaller than the anions. We all know about that. Cations are smaller than anions. So size of cation is less than anion. Okay. So this is a very important property of an ionic solid. So cations are smaller than anion first, and each cation is surrounded by coordinated anions. Each cation is surrounded by coordinated anions, which form a polyhedron. Okay. The sum of the ionic radii determines the cation anion distance. If you see this figure, this is small ion is cation and the large ion is anion. And the sum of their ionic radii R plus, anion means R minus, and cation means R plus. So R plus R minus gives you what? Gives you the cation anion distance. While the cation anion radius ratio, which is R plus by R minus or RC by RA, which determines the coordination number. Coordination number determined by the this ratios. We can see this is a coordination number with respect to the radius ratio list according to their polyhedron sizes. Okay. So all these things are told in rule number 1, the Pauline's rules. You can see that for coordination number 6, in this figure, you can see this is uh, 4 cations are placed in the surface plane, and 1 cation is placed above and one is below. So this constructs a what? This constructs a octahedral symmetry. Okay. So here, but which will be stable and which will be more stable or which will be unstable? It depends completely on the position and size of the cation. Okay. So if the size of the cation is very small, which is positioned at a very small interstitial void between the anions, then it is unstable. Okay. And if it resides completely covering the void, then it is a stability limit. And from here, the stability limit increases. Okay. Next, the stability limit increases when this anion size is bigger. So when the cation and anion radius is getting bigger, so it is going to be stable because the separation between anion and cation means the separation between the similar ions is increased. So the repulsion forces between them is decreased. Okay, and then it is going to be stable material. In this figure, you can say the sodium chloride structure. Okay, small ion or cation, that is sodium ion, and bigger ions are chloride ion. So each chloride ions are covered, 4 chloride ions are placed at a plane, this plane, and at each chloride ion above, and this is forming a octahedral lattice. Okay. Similarly, cesium ion for cesium minus plus and chlorine minus. So this is a bigger ion. This is a bigger ion placed in this position, and cesium ion placed in this position. But here, so why I have shown sodium chloride and cesium chloride separately in this figure, because of that their radius ratio. You can see, if you can see the radius ratio of sodium chloride is 0.55, which forms octahedral position, but octahedral coordination. But if we see the cesium chloride radius ratio 0.93, which is 0.93, which is, so this forms a cubic structure. So which is more stable? Cube is more stable than octahedral position. So cesium chloride is most stable than sodium chloride. So all these, according to the radius ratio rule, are told in first law, first rule of Pauline's. But second rule of Pauline's states it's mainly the charge neutrality rule. If any solid like MX and Y, MX is cation, is anion, and there valence is there. Sorry, there are atomic numbers are there. It is up there. How many types of numbers of atoms are there? Solid is charge neutral anytime is going to tell its second rule. And second rule mainly telling about electrostatic bond strength, which is determined by the S, which is nothing but the charge and the coordination number. And anion charge also be determined by the epsilon value. Epsilon is nothing but the summation over all bond strength. Okay. So from here, bond strength and anion charge can be calculated, and a charge neutrality concept is also be confirmed from this rule. And third rule is sharing of polyhedron corners. Sharing of polyhedron corners, edges and faces. So corner linking polyhedron is preferred over edge or edge sharing to ensure a larger separation between the atom. If we consider are uh, tetrahedral atom like this in position, and in this position there is also then we can tell that we can tell that if they are uh, share their edge sharing means they are placed with their edge sharing, not in their edge sharing, then the distance will be maximum. And we need the maximum distance because of reduced repulsion between the anions and cations. So this is third. And what the fourth rules is telling, crystals containing, okay, fourth rule, crystal containing different cation. Okay, just like olivine, different cation. M is one cation, this silicon is one cation, another cation. So, if any solid contains different cation, what rules will be placed and what type of rules for formation of ionic solids has been taken and has been obtained, has been maintained, will be maintained, like barium titanate. Here, barium is has +2 charge, titanium has +4 charge. Okay. So all this depends on high valency and small coordination number. Which have high valency and small coordination number. They do not share polyhedron formed by them with one another in the material. This is one of the most important properties of fourth rule. We can see that M ion, magnesium or ion, blue spheres, the silicons are purified. So silicons, they have higher valency, +4 valency. Silicon has +4 valency, and magnesium or iron like they have how many valencies are there? +3 or +2. Okay. So in these cases, higher valencies will be preferred, and they do not tend to share their polyhedron elements with one another. So ultimately, this will be a stable element inside the material. Okay. Next is fifth rule, and I will at last I will at last tell about summing up all the rules. So what the fourth rule of parsimony tells about, the number of essentially different kinds of constituents in the crystal tends to be small. The repeating units will tend to be identical because each atom in the structure is more stable in a specific environment. Okay. So different kinds of constituents in the crystal tends to be small. Like here you can see only one kind of polyhedrized, that is tetragonal structure. But there is a tetragonal also and octagonal void. Also octagonal structures also there. Octagonal structures is also there. So this rules is telling about different kinds of constituents in a crystal structure tends to be small. So you cannot take this structure. We are happy with this. Okay, the crystal is happy with this. Okay, so first law is telling about the position of cation anion and their atomic anion radius size and ratio. Second law is telling about the bond strength and their valency. Third rule is telling about the corner sharing. Fourth rule is telling about small cation coordination number and large valency. And fifth rule is telling about the not similar type of or not many different types of structure like polyhedron, tetrahedron will be eligible. Okay, so based upon this five laws, we can now answer the question number one. Does cation and anion sublattices always have same lattice, crystal lattice? It's acceptable, it's true. And next is Next is, okay, next is anion makes the base lattice. Of course, anion makes the base lattice, and cations occupy their interstices. This is also true. Cation anion sublattices may have different crystal structure. No, they always have the same crystal structure. They always lie on same crystal structure. They resides in the same crystal structure. So this is not clear. And cations and anions are as close as possible to each other. This is also true because they all always try to be stable structure and they always try to be uh, as close as possible. We have so seen in all the rules of the problems. Okay, so that's all, and we can now move to the question number two. Okay, identify the disorder in the following figure. You have already learned about the disorder present in the crystal structure. How many types of disorder, what types of disorder present? Based on this question has been made, and this larger ion is anion. Larger is anion, okay, and smaller ion is cation. This is cation. Okay, so here four options are given here: substitutional, Frenkel, Schottky, non-stoichiometric disorder. You have to learn about disorder. Okay. Okay. Now you can see that what is the substitutional defect? What is the substitutional defect? Okay. Now this is a perfect crystal where every atoms are arranged periodically at their lattice site. Okay. You can see at their lattice site. Okay. Now, if a foreign atom replaces the original atom site, here this atom has been replaced by this red colored atom and occupies this lattice site. Okay, then what will be? This is called the substitutional atom. This is perfect crystal, but this is not perfect crystal. This is substitutional atom. Okay, so here this type of incident is not occurring. Here is just replacing this cation is this cation position is replacing to this is replaced in this position. This is interstitial position. What is the interstitial? Interstitial position is the position between anion and cation position. This is the void position. Okay, these are the interstitial positions. These are not related to the atomic positions. Okay, so this is not related with the interstitial position. So substitutional disorder is not the correct option. Next is Frenkel disorder. So Frenkel disorder, you can see this is a sodium chloride crystal. Chlorine atom is higher, has larger radius than sodium atom. So in this case, Frenkel disorder, you can see this sodium atom is replacing at the interstitial side. This is called the Frenkel disorder. Okay. Or next one type of disorder, Schottky disorder. Schottky disorder is what? Schottky disorder is two oppositely charged ion leaves from the lattice side. Here, two oppositely charged ions are sodium and chlorine. Okay, so two oppositely charged spheres, if two oppositely charged spheres leave from each side, and this color you can see that chlorine has been left here and sodium has been left here. Means they simultaneously will leave from these two sides and left the um, crystal into a neutral form. There will not be so will not be shown with charge difference. Okay, charge neutrality. So charge neutrality will always be present there. Neutral charge will be there. Okay. So both chlorine and sodium will be left there. So this type of disorder is called the Schottky defect. And these are some sources from our technique. These figures And next is the non-stoichiometry effect. What is stoichiometry? Stoichiometry is the number of cations and anions are not being disturbed. Means uh, if sodium atom is replacing here, then no charge neutrality has been disordered. Means no extra sodium has been put or no extra chlorine has been put in the figure, in the unit cell. In this case also, we have removed just one sodium and one chlorine. We have not put anything extra excess of sodium and chlorine. If this happens, means different from the actual stoichiometry formula that happened, means the ratio of the number of one kind of atom to that of the another kind of atom arises, then this defect is called the stoichiometry defect. You can see this is non-stoichiometric nickel oxide, where a vacancy has been formed here, means a nickel ion is missing there. Nickel ion is missing there. Similarly, in zinc oxide, excess of zinc ion has been placed here. So it can be missed or it can be accessed here in the atomic crystal. Okay. Here you can see electron has been placed here. So electron or any ion or any vacancy, everything are responsible for non-stoichiometric defect. So, okay, so you can now answer this question, question number 2, that it's telling about what type of disorder is this. This is nothing but Frenkel defect because one cation is shifting towards interstitial side. Okay, so we can now go forward to question number 3. Okay, so what question number 3 is telling about formation of charge defects in a crystal leads to following situation. What? If a charge defect, what type of charge defect? It will be point defect, stoichiometric defect, zero-dimensional defect, Frenkel defect, okay, or non-stoichiometric defect happens in the, so not non-stoichiometric, only stoichiometric defect, only stoichiometric defect, okay, only stoichiometric defect, okay. If this type of defect occurs in the crystal, then what happens? Solid becomes negatively charged? No. Charge neutrality is also always present in the crystal. So solid remains charge neutral. This option will be correct. Becomes positively charged? No. This will not be correct. Solid can be either positively or negatively charged. No. This also. Because you can see that for point defect like Frenkel and Schottky defect, for Frenkel defect, what we have seen? For Frenkel defect, you can see that this green, sorry, this blue ball, this is sodium chloride, if you can see, blue balls have been shifted to this interstitial source, that is Frenkel defect. But no extra positive or negative charge has been created inside the crystal. So this is charge neutral. The cation vacancy, cation's interstitial, they occurs together. This is Frenkel defect. And what is Schottky defect? Here is also charge neutrality is present. Remove one cation, here one cation has been removed, and one anion has also been removed here. This type of anion has been removed here. So this is Schottky type of defect. Okay. So in this case, no extra charges has been present here. No electron has been present here. No holes has been present here. So charge neutrality has always been present in the crystal. Okay. This is very easy question. And the next question number 4. Question number 4. Okay. You can see the defect reaction. These are some defect reaction. Okay. Reaction means there is a left hand side and right hand side balance. There will be left and right hand balance. Okay. The defect reaction for electronic composition compensation upon formation of oxygen vacancy. Here oxygen vacancy is found. This is called oxygen vacancy. Okay. Oxygen vacancy is there, then which defect reaction is true. Okay. It may be one option or two option correct. This is the position of oxygen. O, O oxygen is present at their oxygen site. This signifies the site position. Okay. And there, this is the oxygen vacancy. V means oxygen vacancy. Okay. So dot represents the positive charge and cross represents the zero charge or the neutral defect. Okay. Everything we can answer this question by knowing the Kroger-Wink notation. By knowing the Kroger-Wink notation. Okay. Kroger-Wink notation. Okay. So Kroger-Wink notation is a set of convention that are used to describe electric charges or lattice position. Electric charge or lattice position, very, very important, lattice position of point defect species. This is mainly for point defect species in the crystal. It is primarily used for ionic crystals and is particularly useful for describing various defect reactions. Okay. And it was proposed by Kroger and Fink. So this is very, very important. Notation. What is the notation of Kroger-Fink expression? MCS. This is MCS. M for M is the correspond to the species. And what is C? What is OS? I will know. We want to know it later. First of all, what is M? M can be atoms. It can be vacancies, interstitial, electron, hole. Atoms like silicon, nickel, oxygen, chlorine. Vacancies can be expressed as V in M. And small v also, where V is the symbol of vanadium. Interstitial, you can express interstitial as I. Okay. In case of N. And for electron E, for electron E. What is the meaning of S? S is the lattice site. From site, S has been taken. And what is the C? C is the charge. What is the electronic charge of the species related to the site that is occupied? And C is represented as cross for null charge, represented as dot for net single positive charge. It should be remembered. And dash for net single negative charge. Okay. So we can now see some example like Al cross. Means an aluminium ion sitting on an aluminium lattice site. Aluminium sitting on an aluminium lattice site. This represents the aluminium ion or lattice atom or ion. Okay. And it is sitting at aluminium positions. Sitting at aluminium position. Okay. And a nickel ion sitting on a copper lattice site with neutral charge. This cross signifies neutral charge. This was also. And a chlorine vacancy is represented by this with single positive charge. With single positive charge. Okay. And calcium interstitial ion with double positive charge. Calcium interstitial ion. Calcium is present is situated at the interstitial position with its double positive charge. Okay. Next is a chlorine anion on an interstitial site. Interstitial site with single negative charge. This is single negative charge. And an oxygen anion. This is oxygen anion on an interstitial site with double negative charge. And an electron, no site is specified. Okay. Next, what is most important property using Kroger-Wink notation? That is, all masses, all sites, and charges should be balanced in Kroger-Wink notation for both intrinsic and extrinsic defect. It is imperative to keep all this balanced. Right? Number of each number must be present, proper number of each ions, that is mass balance. Equal number of sides must be equal exist, that is side powers. Sum of the charges of the reactants and the products must also be equal, that is charge balance. Okay, so everything should be balanced here. Everything should be balanced. And see. Okay, now for Schottky and Frenkel debate, to begin the Schottky and Frenkel debate, we can start with null reactant 5 and produce either cation anion vacancy, Schottky, or cation anion vacancy and interstitial, that is Frenkel. To start with Schottky defect formation in titanium dioxide, what will be there? Titanium is 4 positive charge, this is negative charge. If a vacancy of oxygen is created, two vacancies of oxygen is created. So this is an oxygen vacancy site with two positive charge. Where oxygen vacancy is created in which place, two oxygen vacancies will also be created. Unit two unit positive charge. So these are four negative charges at the titanium vacancy site also. This is Schottky defect. For barium titanate, this is two positive charge, this is four positive charge. So, two negative charges vacancy at barium site, four negative charges vacancy at titanium site, and three positive charges oxygen vacancy at oxygen site will be formed by balancing it with neutral null reactant. Phi is null reactant. Sometimes phi is also denoted as 0. Okay. And next is Frenkel disorder. In Frenkel disorder, you can see that at magnesium position, oxygen position, they are presented as a null neutral charges. After Frenkel disorder, what will happen? If anion magnesium is raised at the position, so your oxygen means anion is shifting at their position to the interstitial section. So oxygen will go to the interstitial position with lefting to neutral charge. So oxygen vacancy will be created there also. Okay. And similarly, this kind of reaction for cation shifting is also there. It will be there. So basic types of some reactions like Schottky defect, phi, like cation and anion vacancy at cation and anion vacancy will be there. Electron or hole for charged Schottky defect. For cationic Frenkel defect, this type of. Okay. Now I am just going to tell about the entropically favored side. Entropically favored side, which involves temperature. If temperature is involved, then no electron must be there involved. So at the rest position of the metal side, if an electron is induced there, then it will be reduced. Similarly, it will be oxidized after electrons removing from this uh, BN side. So B is also a cation side. Okay, so these types of defects can be found here. Now, you can easily solve the problem regarding this defect reaction. First, this tells about the oxygen is placed at oxygen side. Okay, oxygen is placed at the oxygen side. So, what will happen here? If one oxygen is left from the side of inside, then one vacancy will be created. So this option will be correct with neutral charge. So here balance will be there. What type of balance? Mass balance, charge balance, site balance. G should be balanced in these reactions. Next, we can say two unit positive charges at oxygen cell. To fill these unit positive charges, compensate this oxygen unit positive charges, two electron has been left out. Okay. So this also is correct. But this is not correct because two electron is not compensated by two unit positive charge of the vacancy side. So charge is not compensated or balanced here. Similarly, uh, in D case, charge is balanced here, site is also balanced here, mass is also balanced here. So A, B, C, A, B, C, A, B and B are correct, C is not correct. Okay. Okay. So we can go to the next question. Question number 5 and 6, they are combined question. So consider the following reaction. In O2, N is cation, which how it is created the vacancy with oxygen acting at the from the crystal side. And what should be the metal? What should be the metal reaction? What should be this cationic position? Okay. So in these cases, we have to mind, as I have told in previously, what balance should be there. What type of balance should be there? First of all, mass balance. Oxygen is balanced there, so there is no problem of oxygen. I have to balance mass of M. And what I have to balance? Site balance of M. Oxygen site has been balanced, is balanced there, but M site is not balanced here. And last is charge balance. Okay. Before proceeding to this question, I'm just going to tell about oxygen reduction. Okay, I will tell it later. First of all, we are trying to give the answer of this question. So we can see that two vacancy oxygen vacancy site has been created. This two, okay, two oxygen vacancy has been created here. Okay, so for two oxygen vacancy, the charges, the unit for these are the two unit positive charge. Okay, so for 2 into 2 will be 4 unit positive charge. So we must have to fill the 4 unit positive charge at which side? At M side. At M side. So you can see that for two oxygen vacancy sites, there must be separate M sites. How many M sites will be there? 4 M sites because of 4 unit positive charge. So 4 unit positive charge will be there and it will gives 4 M plus at M site. This is the M site position. So 4 M plus at M site position gives this answer value. Okay. For solving the next question, for if any defects could fall, such an oxide, in oxide, which will be true? There are 4 options. To answer this question, we need to know about the oxygen reduction tree. This is iron, this is anion, this is cation. Okay. So oxygen reduction tree for simple ionic compound X What will be the oxygen redox effect? It depends on the cation to anion ratios. Cation to anion ratios. What will happen if greater than 1 and what will happen if less than 1? Greater than 1 is signifies about the reduced in time and less than 1 signifies as the oxidized. I'm not going to details in these cases. So for these cases, metal excess will be happen. If metal excess happen, what will happen? Anion deficiency happen will be there. So what 1 plus y means at cation position, some cations happen industrial. And similarly, 1 minus 1 will be there to balance. So anion deficiency will be there. And vice versa, the reverse properties will be shown in oxidized cases where anion excess and cation deficiency will be found. So what will be the quiz for this defect? For an oxide, this is reduced. Okay. So for reduced, metal excess will be there and oxygen deficiency will be there. So these are the correct answer. Okay. These are not the correct answer. Okay. So I'm just checking this present paper. You can see now what is the next question. Next question is question number 7. If any question arises, please tell. Okay. Defect reaction for shortcut disorder in N2O3 can be defect reaction for N2O3. So this is minus 2 and this will be plus 3 charge. Plus 3 charges will be there. If oxygen vacancy is created there, oxygen vacancy is created there in oxygen position. So oxygen vacancy is created for oxygen position. How many oxygen vacancies will be created? For 3 atoms, 3 will be created with 2 unit positive charge, and it will be balanced by 2 metal M vacancy of M at inside with 3 unit negative charge, and so that this charge is balanced 2 into plus 3, minus 3 and 2 into plus 3, that 3 into plus 2, that is 6, that is plus 6, and that is minus 6. So charge is also balanced there, site is also balanced there, and their mass is also balanced there. So where this is nothing but null reactant, phi or 0. Okay, so A is correct here. From there you can see that A is correct here. Oh, okay, see again now. So okay, we can now go to the question number 8. So I have done all the questions like first 1, 2, 3, 4, 6 up to 7 question I have done. If any question, you can tell about any question. Okay, so let's say that okay. So I am going to okay. Question number 6. Question number 6. Question number 6. Okay. Why not question number 6? Option 1. Which option? Okay, option one. Student question number 5, 6. Okay, stoichiometric oxide. Okay, this is so stoichiometric oxide is like Frenkel defect and so in this cases Frenkel defect and for Frenkel defect, Schottky defect. Okay, in this cases charge are neutral. Okay, charge are neutral charge. Okay, neutral charge. So we cannot uh, tell that these defects are formed by oxidation and reduction reaction. Okay. In oxidation and reduction, there must be involvement of charge, positive negative charge. Okay. Okay, so we can go forward to next question. Okay, thank you. Okay, ठीक है. Next is question number 7, 8. Identify the correct defect reaction after substitution of calcium oxide in zirconium dioxide. Okay. So in the zirconium dioxide structure, this is a cubic structure. This forms a cubic structure. If you see its crystal structure, you can see that it's a cubic structure. And if we drop calcium oxide in the zirconium dioxide crystal, then what will happen? It will occupy the zirconium site. Calcium will occupy the zirconium site. Okay. So when calcium occupies the zirconium site, then zirconium site will be written as like this. Okay. So here oxygen vacancy will also be created. Okay. So oxygen vacancy will also be created, and for this oxygen vacancy, two unique positive charges will also be created. After for calcium dioxide, oxygen vacancy for only one unique positive charge will be created for only oxygen, and only one oxygen will be removing out at the oxygen position. Okay, after creating the calcium. So two calcium ion will not be there. Calcium only one calcium ion will be there at the zirconium position. You can see that zirconium oxide with calcium oxide protein. After calcium oxide protein, calcium is occupying at the zirconium position, which two unit negative charges, letting one oxygen vacancy, which two unit positive charges, and only one oxygen vacancy. Sorry, oxygen with neutral charge will let go. So this all will happen when calcium oxide will be dropped at zirconium position. Now we are trying to see that what's the structure of zirconium. This is the structure of zirconium dioxide structure. This structure. This is a cubic structure. You can see this is a cubic structure formed here. Okay, cubic structure is formed here. Found here. And it is at each cubic structure position, oxygens are arranged octahedrally. Octahedrally. Okay. In zirconium dioxide position. Here, uh, these are zirconium and these are oxygen. Okay. Next, when we drop calcium oxide, calcium oxide over here. If we drop calcium oxide here, what will happen here? You can see this zirconium oxides has been occupied by this calcium position. some position has been occupied by the calcium position. So this is calcium to zirconium. Okay, this is zirconium. So this is calcium to zirconium. We can see that this position, of calcium to zirconium, and oxygens are octahedrally arranged in each unit cell, in corner sharing unit cell. Okay, at the face centered also. Okay, so all these are calcium group zirconium, and we can see there how their vacancies are created, between one oxygen vacancy with oxygen at their oxygen position and calcium. Okay, so correct answer is D. Correct answer is D. Because here everything was balanced. Mass is balanced, charge is balanced, means site is balanced. Okay, in other cases, nothing are balanced here. Okay, next, let's do the question number 9. Okay, so which of the following statement is correct? Is or correct? Which of the following statement is correct? We'll see the question. Just 1 minute. Take me some water. Which of the following statement is correct? This is mainly telling about the defect concentration in a crystal. Defect concentration in a crystal. How defect concentration behaves with increase in temperature. How it behaves. If it increases or if it decreases, then what changes are observed in defect concentration? Okay, we will any problem. This recording is fine. Okay. Okay. If you want to ask any question, you can ask. Okay. Let's see if already it is visible. Question 9. Okay. So to answer this question, we have to know the concentration, how concentration is dependent. Okay. We can now let's solve. We have taken an option example of magnesium oxide, and for this magnesium oxide, only Schottky reactions is maintained there, means both magnesium and oxygen, both magnesium or oxygen are displaced from its atomic position. Displaced from its atomic position. Okay. So what will happen if those two are displaced from its atomic position? What will happen? So this is the null reactant for any point defect reaction. We use this symbol, that is the null reactant symbol, and a magnesium vacancy is created and oxygen vacancy is created. Note that this vacancies on the magnesium sublattice has -2 effective charge and the vacancy in the oxygen sublattice has +2 effective charge. Now we have to use the famous law of mass action. So after using the law of mass action, we know the law of mass action consists of an equilibrium constant, which is denoted by K square K. So what will be the equilibrium constant? What will be the equilibrium constant? Is nothing but the multiplication of the concentration of each vacancy, means cation vacancy concentration and oxygen vacancy concentration. So by using the law of mass action, we can calculate the temperature dependency. Now, based on the above reaction, the stoichiometric reaction is this. Stoichiometry of this is stoichiometric defect. Point defects are always stoichiometric. Means the number of defects, cation vacancies, and number of oxygen vacancies are created will be same. So there, at equilibrium, their concentration will also be equal. Okay. So now also the equilibrium concentration constant, K is the equilibrium constant, can be related to the, we know, this is related to the Gibbs free energy, delta Hg. How they are related? They are related to the delta Hg by kBt in the exponential form. Kb is the Boltzmann constant, we already know it. And how delta G can be represented? Delta G is nothing but delta H and T delta H. Delta H is enthalpy of the reaction. That reaction. Okay. And this is what? This is the entropy of the system. Okay. So G depends on H, enthalpy and entropy. So by comparing, okay, so by comparing these two equations, means this K value and this K value, we can say that as they are equal, so we can write it as a square value. Okay. So from this, you can say it is equal to 1 by root 2, means 2 will be there. And delta G is replaced by delta S and T delta S. Okay. And this gives A into exponential of this. A containing the entropy term. Because this is constant here. Okay. So A into delta H, this gives the concentration of EMG, concentration of the vacancy is directly proportional to the exponential of 1 by T minus 1 by T. Okay, exponential of 1 by T means when temperature will be increased, this term will be temperature will be this term will be decreased, but exponentially it will be increased. Exponentially it will be increased. Okay, temperature is increased. Temperature increase UMG increases. Okay. So these are the concepts. So what will be the answer of this question? The defect concentration increases exponentially with increase in temperature. With increase in temperature is will be the answer of this question. Okay, there is a question for question number 7, option 1. Please tell the reason. Okay, just wait. For question number 7, for question number 7, okay. Here only the charges vacancy, the balance has been created here. Balance has been created. What type of balance? Mass balance, charge balance, and site balance are created here. If three oxygen vacancies are created with two negative for each positive charge after vacancy is created, then this charge will be +6. Then to compensate this, we have to create three metal vacancy, M vacancy, sorry, cation vacancy, whose charges is -3 negative charge. So negative charge is also there. Site is also balanced here. Mass is also balanced here. Okay. Okay. So okay. Have you understand with any problem? No. Any problem? Okay. Now, okay. So, okay. So we are here. Question number 9. Defect concentration increases with exponentially it increasing, not in linearly. Actually, temperature increment increases the defect concentration because of the vibrational effect of the temperature, increases the energy of the atomic sites. Okay. So that's why temperature increases the defect concentration and it increases exponentially due to the effect of Gibbs free energy. Okay, Gibbs free energy contribution must be there. Okay, we are moving to the next question, question number 10. Question number 10. Okay, Ni, if Ni, Nv, and N, number of cations, number of vacancies, and total number of lattice site. So, total number of lattice site is nothing but number of uh, anion vacancy, number of vacancies, cation interstitial, and number of, sorry, this is cation interstitial count, cation vacancies for, okay, and total number of lattice sites. So these are not related, okay, these are not related. Okay, actually, what happens is this is the cation site, this is the anion site, cation, this is cation, this is anion, again this is anion, again this is anion, this is cation, this is cation. Okay, so in between them, those are interstitial sites are there. So the number of ways to arrange the vacancies in the solid is of the Frankel defect. In Frankel defect, what will happen? Cation anion will be interstitial site. Interstitial site, okay. Cation anion movement to the interstitial site. Okay. So how many number of ways they can arrange there? How many number of ways they can arrange there? Cation site arrange. This is standard W. This is Frenkel disorder we have seen earlier. And I'm just understanding this thing that this cation is shifting to this position. This is Frenkel disorder. Frenkel disorder. Now, if NV is the vacancy, AMI is the interstitial number. Okay. So this type of disorder means Frenkel disorder, which results in equal concentration, of vacant lattice sites and interstitial happens for the Frenkel disorder. We are all know about this. As the extent of this kind, this is disorder is increases disorder. So structural energy is also increased. Structural energy is also increased. That's why delta G has been considered here. Is HP. I'm not going to details here. But at the same time, entropy means randomness of the increases. Randomness must be increases there because now this type of vacancy is created and this is shifting towards this side, interstitial side. So similarly, from this relation, delta G equal to delta G naught, N delta G, and T delta G. This is entropy set, and this is the HP energy. Okay. So this N delta G, free energy change. This is called the free energy change necessary to create A interstitials and vacancies. Okay. This record. Okay. Now, so there are 10 normal sides, an equal number of interstitial sides. So they are in normal side bigger if there are in normal side. Normal side contains cation's position, anion position, then there are equal number of what position? Equal number of interstitial position is also there. Interstitial position. Okay. So the interstitial side can be arranged as factorial N. We all know this. N minus N factorial N factorial. And similarly, we can arrange also the vacant side. That is nothing but n factorial minus n minus nv factorial by nv factorial. Okay. So for vacancy, if there are n side and nv is the vacancy side, so first of all, how many times we can arrange n factorial? We can arrange n as a n factorial. N side we can arrange n side in n factorial times. Okay. And for this n factorial time, how many times of voids can be arranged? This can be arranged by the this n minus nv factorial and nv factorial. We can arrange nv is that's the nv factorial and nv minus nv factorial we can arrange nv sides we can arrange this time. So in result we can arrange this. Okay. So what will be the answer? Answer will be n factorial divided by this. Answer B will be correct for his question number 11. Okay. Question number 11 is the point defect. Question number 11. Point defects are four options. Point defects, you already know about the point defects. How many types of point defects are there? So point defects, what properties they show? First, are they thermodynamically stable or unstable? They are important for charge conduction or not. They are affected by temperature at which materials is kept, or they are not affected. Okay, so first of all, they are thermodynamically stable. How? So we can try to find out this answer, how the point defects are thermodynamically stable. Because the formation of the point defects like vacancy increases the entropy of the crystal. Entropy of the crystal increases. Yes. How they are increased? We will tell that using the Gibbs formula, Gibbs free energy formula. Delta is equal to delta H, which is enthalpy, T is at use temperature, and it's active, and delta is the entropy increment. Okay, so the famous question arises here: why the point defects thermodynamically stable but dislocation is not? Dislocation possesses very high energy. Dislocation means the other atoms removes the original atomic position of the crystal and occupies that position. So in these cases, large energies are formed in dislocation process in compared with point defects. Okay. So the large dislocation line energies thus render them unstable in the crystal. But if these are the crystal structure and if line dislocation occurs, then it will be dislocated from this line or from any surfaces. So in these cases, much energy will be dissipated. Okay. Mass energy will be dissipated here. So you cannot consider it. Okay. So to show why the point defects are thermodynamically stable, in these cases, we taken GV. HV is the enthalpy, enthalpy increase for the presence of vacancy, and entropy change for vacancies only. Okay. So NV, vacancy introduced in the crystal. And what is N0? N0 are the atoms. They are bringing about the free energies. And I am not going to discuss the details. You already learned about this and how GV can be calculated with NV and the T. And at last, you can see this type of relation. In NV equal to N0 to the power means then the vacancy is the vacancy number. Okay. NV is the vacancy introduced into the crystal. So how many numbers of vacancy introduced in the crystal? That is vacancy is type of a point defect. Type of a point defect. So how many numbers of vacancies has been created in the crystal is directly proportional to the exponential value of HF divided by KT or RT. Okay. So HF is the work to create 1 mole of matrices and R is the universal gas constant. Okay. R is nothing but R is related to K, K is Boltzmann constant. Okay. So the reason vacancies, this is the very most important line. You can see that the reason vacancies are thermodynamically stable is that whereas the crystal enthalpy does increase with added vacancies, at the same time the entropy decreases such that the overall free energy curve attains a minimum value. Okay, you can see this type, this. This is the free energy curve, that is G curve. This is plotted here. Right? Vacancy number and is plotted here. We can see G value is increased. It is 0. And this is exponentially decreased yet for the entropy. This is entropy. And in result, you can see this type of graph. This is showing what? At equilibrium vacancy amount. Okay. So the this free energy curve flattens at a certain point. This is the equilibrium vacancy amount. At a certain point, equilibrium vacancy amount this is called. If the temperature were lower, then this equilibrium vacancy condition would decrease. Vacancy condition would decrease. Higher temperature produces greater vacancy amount. Okay. So the point defects are thermodynamically stable. They are thermodynamically stable. Okay. So, and why this location are not equilibrium? Because their strain energy is too high. Consequently, distribution raises the free energies of the piston and thus they are susceptible to metallurgical accuracy. This tendency to lower free energy results in distribution. So, this option is correct. That point defects are thermodynamically stable. They are thermodynamically not stable. This is incorrect. And point defects are important for charge conduction. This is of course true. And these are affected by the temperature at which material is kept. We have seen that M varies as exponential value of 1 by kBT minus 1 by kBT. So it directly affected by the temperature. Okay, as you can see, for charge conduction by the point defect terminates when the band gap is too large. Band gap is too large between conduction band and the valence band. Conduction band and the valence band. Too large. These point defects help to conduct to decrease this band gap. Okay. So this is told here in point defects and effect of temperature on the point defects. We have already shown here that the point defect concentration of magnesium dioxide for magnesium. This is expected. Okay, so this is directly proportional to the exceptional values of the temperature. Okay, so three options are correct for point defects here, and this is unstable, not unthermodynamically unstable. This is not correct. Now, question number 12. Sphalerite, that is zinc sulfide structure. Compounds have following attributes. Zn structured compounds have following attributes. So we have to know sphalerite or Zn structure. Okay, so we have to know the Zn structure. This anion form FCC lattice, cation form FCC lattice, coordination of anion is 6. So we have to know what type of structure of zinc sulfide contains and what is the coordination of anion or cation. So in Zn is this is negative charge and positive charge. Okay. So they are coordinated by this is a FCC lattice. This is a FCC lattice coordinated by the 6 coordination number as their cationic and anionic radius Zn2 plus by source nearly 4.14. So 6 coordination number of the cations. Cation has 6 coordination number, but why not for anion? We have to see the figures also. Okay, we have to see the figure and what is the orientation of anion and cation and how they are oriented at face centered cubic and C. So I have collected the sphalerite figure from the Wikipedia and see this is the sphalerite structure. Okay, You can, if you observe clearly, you can see this type of crystalline structure. Crystalline structure. Okay, this type of crystalline structure it present here. Okay. So this is fullerene. So mainly, so sulfide material. This is sulfide material category. ZNS. And iron is also there. This is the general formula. ZnX Fe x minus 1 S. And this ranges from 1 to 0.6. So when x value is 1, it gives Fe 0. So ZnS will be there. Okay. And occupy the face-centered position. Face-centered cubic lattice. Okay. For x equal to 1 for pure ZnS. Okay. With two lattices displaced from each other such that zinc and iron are tetrahedrally oriented. What tetrahedrally oriented? How they are oriented? We will see now. And I have created a structure of Zn and S. This is zinc, small iron, and anion, cation, and the large anion is sulfide cation, sulfide anion. So this is the unique cell. You can see the unique cell here. You can see the unique cell here. And this is the unique cell. This is the unique cell. These are the sulfide ion at its corner. At each corner, it is sulfide ion. Okay, and at each face, at each face facing, at each face, sulfur ion was also there present. So this is a face-centered cubic lattice. Face-centered cubic lattice for sulfur, and each zinc ion are occupied tetrahedral. Each zinc ion occupied tetrahedral. So what is tetrahedral arrangement? If three atoms situates at this one slide, a void is created in between them. Void is created in between them and place an atom. If you place an atom, then this type of structure you can see tetra means four face structure. Okay. So tetrahedral arrangement sources for each connecting each oxygen atom at each oxygen atom, four oxygen atoms are there. Sorry, zinc for Zn plus are tetrahedrally arranged with centered at sulfide. At each face center also sulfur are situated. And each zinc atom, you see this, and this, and this. Okay, so each zinc atom also forms FCC lattice. So cation and anion both forms FCC structure. Both forms FCC structure. Okay. So cation and anion both form FCC structure. Next, cubic ZnS of zinc blend. The radius is 0.85. For anion radius 1. So what is the radius ratio? 0.48. Very important point for ZnS. The cation anion radius ratio is 0.48, and which is lying between 0.414 and 0.732. Hence, this is octahedral structure. and 0.73 is cubic structure like caesium chloride. So octahedral coordinates of 6 is 2 minus around a zinc 2 plus. Is it possible? No. Is it? This is not possible now. We can, but again, you can see that there is a difference for the cubic structure and a tetrahedral structure. You can tell that there is six coordination number for anion. Sorry, for cation, but not for anion. For cation, for zinc only, but not for S2 names, not for S2 names, because of this radius. So only Zn2 plus have six coordination number. Plus this, so tetrahedral coordination means 4s2 minus iron around Zn4 will be there, must be there. Okay. Now you can see example of a diamond cubic structure and a cubic Zn structure. How they are different. How they are different. So in diamond cubic structure, every atoms are carbon and every atoms are similar. Every atoms are similar atom. But for ZNS, they are not similar. They are this S2 minus atom ion and Zn2 plus ion. Okay. So different types of ions will be there. So structure must be different. This is pure cubic structure. The FCC lattice. Okay. This is FCC lattice where carbons are present at each corner along with its faces. Also at the tetrahedral position, 4 tetrahedral position. What the position? So two carbon atoms at motif, motif and lattice point. You know, lattice point are different from motif. We can say it as a lattice point, but not motif. Okay, lattice points. We can say it at lattice points, but not motif. But motif means it contains one or more atom. One or more atom at each lattice point. At if not lattice point, it's a motif. Okay. So here one point, one lattice point, and here is also lattice point. Here is also lattice point one. So how they are at 0, 0, 0, carbon is present there, and at 1 by 4, 1 by 4, 1 by 4. This is 1 by 4. This is 1 by 4. This is 1 by 4, 1 by 4, 1 by 4, and this is 1 by 4. You can find one carbon atom. Similarly, similar structure has been found in ZNS. ZNS crystal structure. How they are similarly, only difference is here zinc, zinc atom, zinc ion is placed there. Zn 2 plus ion is present there. At which position? At tetrahedral position. At tetrahedral position. Zinc atoms are placed at tetrahedral position. So the coordination of S2 minus is at 0, 0, 0. These all are 0, 0, 0. And similarly for carbon at the diamond cubic and zinc 1 by 4, 1 by 4, 1 by 4. Or 3 by 4, 1 by 4, 3 by 4, 1, 3 by 4. This type will be arranged for 4 atoms inside the one unit cell. Okay. So these are the some information for ZNS sphalerite. So based on this information, you can now answer the question that sphalerite ZNS structure compounds have the following contribution. Anion of course form FCC structure. Cation is also forming FCC structure. Okay. Anion is also forming its structure, cation is also forming its structure. But anion has the coordination of number 6. This is not correct. But the cation has the coordination number of 6. This is correct. Okay. So these are the all information about ZNS. ZNS. Okay. Next, we are going moving to the next question number 30. Question number 30. In inverse phenol structure AB2O4. एक होता one is phenol structure, another is inverse phenol structure. We know about that. So for inverse phenol structure, this is the formula of spinel structure formula. Clear. So for inverse spinel structure, which will be true? Okay. Before attempting this question, we can find some uh, information about spinel structure. The spinel structure, the formula of spinel structure is AB2O4, where A is 2 positively charged, B is 3 positive charge, 3 valency, 3 plus valency or 2 plus valency, and O4. So AB2O4. It can also be written as AO, insulin oxygen tension is there, and B2O4. Okay. And everyone are FCC packing of atoms. Every spinel structure are FCC structure. Face-centered cubic structure that anions are present at each corners along with at its faces, which constructs tetrahedral and octahedral position. This is very important. So here anions means O2 minus resides at FCC position, means at corner and at faces, 6%. Okay. And along the there, so where A and B fit, A and B is situated, where? Okay, now see, partial occupancy at both tetrahedral and octahedral side. A B situates at tetrahedral and octahedral side. How they are situated at 1 by 8 tetrahedral and half per unit cell. For per unit cell, 1 by 8 and 1 by 2 for octahedral side. If we consider 8 FCC crystal made up by oxygen ions, so if you can see one crystal structure like this, so this is a crystal structure like one position. You can feel this with 8 this side, this side, this side in ground, and above also 4 will be there. So 8 FCC cell must fill one corner. Okay. So one unit cell for one unit cell. So for one unit cell, 8 FCC cell will be there. But in spinel structure cases, made by oxygen ion at 222. So big structure contains oxygen. How many types of oxygen in the there? 32 oxygen. Because 4 into 8, 38 for 1 8 contribution. And for half A contribution, we will to 4, 12 to 8. So this and 16D atom. 16D atom will be there for B2. Okay. As 2 atoms are there. So depending on spinel structure can be normal or inverse structure. So one is AB2 for normal spinel structure and another is inverse spinel structure. How they are different. Although chemical formula is same, A is 2 positive charge, B is 3 positive charge. But how to are different? Okay, we can now find out. But examples are many aluminate like magnesium aluminate, iron aluminate, cobalt aluminate. Okay, these are spinel ferrite. Spinel structure. Ferrite is for no, inverse spinel. Okay, in this structure, A occupies the tetrahedral side, B occupies the octahedral side. That is very important. How they are occupied, I will see in the next figure. Cation, anion, minus 3 by 6 because of charges at it. Okay, and so oxygen vacancy will be 2 oxygen valence. It is simple mathematics. And for inverse structure, formula is same, but can be more written as so because B is situated at 2 B atoms are there. Okay, for in AB2O4 structure, 2 B atoms are there. And in these cases, one B atom will go to the tetrahedral arrangement and one B atom will go for the octahedral arrangement in inverse spinel cases. This is the difference between spinel and inverse spinel case for the arrangement of B only. Now you can see this figure structure of the AB2O4 spinel structure with general structural tree AB2O4. So oxidation states of 0 plus 2, P is 0, P is plus 3 oxidation state. Yes, so it's neutral at first. FCC stacking up protein. We already have told that 8, you can see that if we consider this as a unit cell, you can see that 8 unit cells are there. To complete a AB2O4 structure, you can see there how oxygen atoms are arranged for magnesium aluminum. This is plus 3 and minus 2. For magnesium aluminum, how they are arranged. This is a tetrahedral structure. This is a tetrahedral structure. And aluminium, this aluminium are forming the octahedral position at each octahedral position also there. So this is forming tetrahedral position, this is forming octahedral position. And this is the unit cell for calculation of the tetrahedral coordinates. Okay, you can see there A atom, B atom, how they are arranged. And in the two besides figure, this is actual and this is inverse. You can see A, C, B layer. Okay, how A, C, B layer are arranged for metal A, B side. Okay, ABC plane. For FCC stacking, this is a spinel structure. And how it is different when A ion and half of B3 ion occupies the octahedral sides. Okay, at octahedral side, you can see this is the octahedral side. Half of A ion and half of B3 ion occupies the octahedral side. And this is the tetrahedral side. Half of B3 ion occupies the tetrahedral side. Okay, this is the difference in inverse spinel structure and the spinel structure. Okay, so what will be the answer of this question? In inverse spinel structure, okay, so in inverse spinel structure, A, B, B also, we can tell like that. So, uh, half of d ion occupies tetrahedral interstices, half of d ion occupy octahedral interstices. These two are correct. All b ions occupy tetrahedral, all b ions occupy, these two are not correct. Okay, I have told in the questions. Okay. Now we are on the verge of this meeting. So it's already 7:47. Only two questions are left there, and only around 15 minutes are left. 10 to 15 minutes are left. And after discussing the two questions, I will go forward for the discussion of question and answer if anyone requires. Then what will be the answer of question number 14? This is lithium niobate is an optoelectric material. Optoelectric material. But why this is optoelectric material? What is optoelectricity? We will try to understand everything. And for optoelectric material, what will be the structure? This is a perovskite structure. Okay, this is ABOX structure. Perovskite structure where A is cation in positive charge. Sorry, not in positive charge. This is a cation. A and B are cation of different valency. Different valency. Okay, A and B are cation of different valency. So A for and this is anion and always oxygen always form HCP crystal. This is correct also. But what for lithium and niobium? Both are octahedrally coordinated or both are tetrahedrally coordinated. If we see, we'll find the structure. What is the structure? And we'll find the answer to give the answer. So first of all, what is optoelectric effect? The refractive index, we know the refractive index of an anisotropic crystal changes with electric field. For if the refractive index changes with electric field, then it shows optoelectric effect. So that is the optoelectric material. If we apply an electric field, you can see there is an electric field is applied and light is passing. So phase or polarization change with refractive index. So there will be a change of polarization will be occurred, and this effect is called the optoelectric effect. Okay, you can also see here uh, if we apply voltage to the electric field between them, between optoelectric material, then you can see in this figure with the application of electric field, M means refractive index is changing like this. Okay, so this type of behavior is observed after application of electric field in the electro-optic material. Uh, means application of electric field, how the optical behavior is changed there, how polarization is changing, due to which the refractive index of the material is changed. This is optoelectric behavior, and this behavior depends on the structure of the material. That's why it is important. What type of structure lithium niobate is forming? This is a hexagonal closed packing structure. Hexagonal closed packing structure. Hexagonal closed packing structure. Hexagonal closed packing structure. You can see at each hexagonal closed packing, this is a unit cell. At each hexagonal closed pack, oxygen atoms are there. Okay. And oxygens are here octahedral coordinate, octahedral arranged by, this is what? This is niobium. So niobium is placed at the octahedral arrangement. And they are also, if you can try to find this, if you can add them, you can find that this is also octahedrally arranged. Lithium. Lithium is also octahedrally arranged. Okay. Okay. So This is the figure where you can see this is ABC reaction. This is octahedrally arranged with oxygen, and this is also octahedrally tetrahedrally. How tetrahedrally arranged? Depending on this concept, now we can answer. This is a HCP lattice, and both lithium and niobium, both ion, are octahedrally coordinated. Octahedral coordination means this is oxygen ion, and this is oxygen ion. And now lithium, or we have shown that lithium niobium pentoxide, niobium ion is octahedrally arranged at the center. Okay. Similarly for lithium also. So this is the octahedral arrangement. Octahedral arrangement. And these arrangement affects the optoelectric behavior in the material, lithium mainly. Okay. So A and D option is correct. D are C are incorrect. Okay. Okay. So we have reached to the last questions, question number 15, and 14 questions have been done successfully. Okay, now my 15 number question, a metal deficient oxide is likely to possess following defects. Metal deficient oxide. This is the term, metal deficient oxide. Metal deficient oxide. So, what is metal deficient oxide and what they possess? Did for and this is not a stoichiometric effect. So, in stoichiometric effect, charge neutrality was there, but here charge is not neutral. Charge is unbalanced here. So in these cases, metal side for image oxide, in this metal side, it is reduced or oxidized, it is reduced or oxidation has reduction or oxidation has been occurred, which has been it we have to find it in metal oxide. So I have collected some data of point defects, which is stoichiometric defect, just Schottky defect, Frenkel defect, interstitial defect. You all know about that. I have already discussed and question regarding question on stoichiometric defect. And this metal deficiency defect, this is metal deficiency defect, are um, in the non-stoichiometric defect group. Okay. So what is non-stoichiometric defect? The ratio of the number of cations and the anions not maintained as shown by the chemical formula. What is the chemical formula? Means there will be some difference. It's 1 plus y or 10x 1 minus y. This type means reduction or oxidation will happen in these cases. Okay. So first of all, we're trying to find the metal excess. Excess means we can see that the term excess means metal excess. First, metal excess cation created by the anion vacancy developed a hole trapping electron. So hole will be developed here. Hole will be developed here. Okay. And if we see this, electrons remain trapped in the anion vacancy. In anion vacancy, electron is trapping there. Okay. And the opposite cases were, and for this, for zinc oxide, this is for case of sodium chloride material, lithium chloride, potassium, and for oxide material, zinc oxide, but cation and electron interstitial states. Here, cation and interstitial also will fail. Metal excess defect due to cation. This is for Zn plus. Okay, so there is Zn plus. And for what is the metal deficiency? Deficiency is found in. So here um, we are interested in metal deficiency defect. So what deficiency is being created here? Created by the vacant site of place current. This is a p-type semiconductor behavior. In transition metal compounds, you need metal source like iron oxide, where iron is missing. Some iron ion is missing there. That's why Fe 3 plus ion constitutes C plus electron. Okay. So, sorry, plus electron. Extra anion vacant site is also available here. Okay. So I have already discussed about stoichiometric defect. So, removal or addition of ions in a compounds, that is called the metal deficiency defect. Some ion or removal addition of ion. Is- So, how they are added or how they are uh, removed. Okay. Next, just like nickel oxide, sorry, nickel oxide, this one position will not be valid. Iron sulfide. Okay. Thus, these are the examples of metal deficiency defect. So, types of metal deficiency defect. Number one, cation vacancy. There must be cation vacancy. Extra ion anion occupying the interstitial site. These also will happen. So, these are two. And also one is hole is created there. Hole is created there. Iron oxide is an example of metal deficiency defect with 0.05 is deficient. You can see these are deficient here. Okay. This is the iron deficiency. Okay. And this like you can see this type of it, iron oxide. Iron is and one hole is there. Okay, electron is moving and this Fe3 is occupying there in this side, in this Fe3 side, Fe2 side. Fe3 plus is occupying there, providing 2 electron required by the excess of the oxygen. For one oxygen, if one anion vacancy is created, so 2 oxygen is required, electron is required. How they are filled? By Fe3 plus. That's right, Fe3 balanced. Okay. So these are the some discussion about the metal deficiency defect, which is under non-stoichiometric defect. So based on this defect, we have approached the answer to metal. So what type of uh, vacancies? There must be metal vacancy, just like iron oxide. Okay. Oxygen interstices for balancing the two electrons. Electrons will not be there, but holes will be there. So these three options are correct for metal deficiency defect. And I have tried to understand every 15 questions of this assignment from question number 1 to question number 2. Okay, it had been discussed. 3, it had been discussed. 4, it had been discussed. 8 is from I can see. 5, 6, okay. But, okay, there is a question from 6. Now, okay. Why this was not correct? Because for the site, for site balance. Okay, this is we have to balance the site. In this case, the site is not balanced. More insight will be there. Okay. So 7, question number 7 has been done, 8 has been done. Question number 9 has been done. Okay, question number 20 is also being done. So okay, so we have reached follow-up to any question. If you have any question, you can tell. Any question? Okay, so now we can end this meeting. See you next week. We can end this meeting.